going through the basics of trapped ions. So like ions, like all atoms, have this internal electronic state. Typically, we label one of these states as our ground state and one of these states as our excited state. And by shining laser light that's resonant with this transition, we can then flop between being in our ground state and our excited state, as shown here. These are some Rabi flops. But additionally, unlike neutral atoms, they're charged, so they can interact through the Coulomb interaction. And that interaction leads to this shared motional mode. So for example, I have here 2 ions. If there were 2 ions confined in our potential, there would be a motional mode along the axial direction where they're moving together and also where they're moving opposite with each other. And this shared motion allows us to transfer energy between individual electronic states of each atom. So we can do things like 2-qubit interactions or 2-qubit gates. And the fact that these shared motional modes are shared between all of the ions in the chain allows trapped ion systems to have high levels of connectivity. So yeah, as I mentioned, we can use this motion to drive 2 ion entanglement gates by driving a carrier transition that's detuned near a motional frequency. And trapped ions have pretty high fidelities for 2-qubit gates. So the typical system will have a 2 ion gate with a 99.9% fidelity. And here on the right, so here on the left is just what that evolution in time looks like. And so yeah, as you can see at the gate time, you have entanglement between your up and down states. And then here on the right, I have a chart of different errors that contribute to this less than 100% fidelity. And so there are things that can cause infidelities like your laser or maybe heating. But by far the largest source of error is from spontaneous emission. So things that we typically term leakage errors. So these are things that potentially you could decay out of your manifold. So you don't decay from, you decay to a state that's not labeled your excited or your ground state, or you can also decay to your ground state. So that would essentially be a bit flip error. Cool, yeah, so that's talking about working with the actual physical qubits. Now, let's say we wanna do something that's actually computational useful, like factoring the RSA 2048. This requires around 10 to the 10 gate operations. And even though 99.9% fidelity is pretty high, that means you do have 1 error per 1,000 operations, and that leads to 10 to the 7 errors if you want to do this. And at that point, that's no longer a meaningful result, right? So we need a way to safeguard against gate errors, which in our system, the dominant source of infidelities when you run long gate sequences is from our 2-qubit gates. And classically, what you do to safeguard against errors is you make a copy of your states. And so yeah, you can just do majority rules every time, but because of the no cloning theorem, right, you can't copy arbitrary quantum states. So what we do instead is we encode our logical state using many qubits, and then by doing certain detection schemes can correct for errors as they come. So a very natural quantum error correction scheme that people implement in trapped ions is what people call the 731 color code, or the STEAM code. This is where you're encoding 1 logical qubit with 7 physical qubits. This is nice because the other error correction scheme that people often talk about is like the surface code, and the smallest surface code that you could implement would require 9. So this is like a little bit nicer. It's a little bit less overhead. Similar to the surface code, you're breaking up your 7 physical qubits into subsections so that we label with different colors. And each color or plaquette has their own ancillas that we routinely take measurements to see if the collective Z or X operators have changed in value. And how we would do this if we're just looking at this red plaquette. So let's say we want to detect a bit flip, an X error, right? If 1, 2, 3, or 4 flips, then we'll measure, and we initialize our ancilla in 0, we'll measure a change in parity, and that change in parity will indicate that something has happened to one of the 4 qubits. Similarly, we have a corresponding circuit that we can encode to detect Z errors. And so it's pretty clear what this gate sequence does when you know the identity involving Hadamard's and CNOT gates, where you're then going to flip any Z errors to a detectable bit flip error that works exactly like the circuit on top over here. And so there, again, you would then detect a change in parity if 1, 2, or 3 got flipped. So yeah, so typically we repeat these measurements often so that we can detect if changes happen in time. And so a typical routine that you'll do is after like a gate operation, you'll measure parity, see if anything's changed, and then a classical algorithm will then determine if something has changed, where the change took place, and correspondingly what corrections need to be made either to the physical qubits or in the software to adjust for that before then moving through the gate sequence. And as an example for how a classical algorithm would then like determine where your error would be, at this top right hand drawing, you can see that if your qubit labeled here 2 experiences an X error, that'll cause the parity of your collective Z measurements on plaquette, the red plaquette and the blue plaquette, to switch sign. Similarly, if you have a Z error on the qubit labeled 5, the syndrome will only be such that your collective X for this blue plaquette will flip. And then if you have a Y error on this qubit labeled 3, that'll cause all of your parities to flip. So that's nice that, yeah, you can isolate which physical qubit was affected and then what to do about it. But there are some things that you can't fix. So for example, there's a bit of ambiguity for a given error syndrome if you allow for multiple physical errors to occur, right? If you have multiple physical errors to occur, you end up having the same error syndrome as if a different single error happened. And so you can't actually correct for more than single errors. And this is fine as long as single errors are much more likely to occur than multiple errors, which is true in general. But it also requires, as I'll talk later on, that any gate operations you have don't allow errors to spread. So if you have a single error, you don't want a gate operation to then cause that to be multiple errors on your qubit. So quickly, just going back to the color code diagram. Here I've already shown previously the different stabilizers used to stabilize this qubit. And here I've written out what the logical Z and logical X and then corresponding logical Y operators are. And if you think about it, because your logical operators are odd and your stabilizers are even, they clearly commute. And so you can do these measurements routinely without changing the value, the logical state that you're in. Additionally, to generate a state, I haven't like written any of them out, but like a logical zero state will be some superposition of many states. And in order to encode that logical zero state requires pretty good connectivity between all of the qubits, which is very natural for a trapped ion system that has things like single ion addressing schemes and shuttling, where you can move the ions that you want to select for to the region where you apply like a CNOT gate. Okay, cool. So now I'm going to talk about fault tolerance. So as I showed previously, that graph that chart that had a bunch of different error sources and their contributions to the total infidelity. So if you wanted, right, a really accurate computation, you could either try and remove all error sources, which is probably not going to happen, or you can just require the errors to be below a certain threshold. And so that's typically what people talk about when they're saying the threshold of a quantum error correction code. You want it to be somewhat high so that that you can reasonably reach it with a physical system. And if you get your errors below such a threshold, quantum error correction will actually help, meaning as you increase the size of your code, your logical errors will go down, or if you increase the number of cycles where you're doing these detection measurements, your logical errors will go down, as opposed to just, right, the longer you run the scheme, your physical errors are going to be more likely. Okay, so I mentioned the service code and the color code. Those are like typical schemes that people talk about. One of the nice things about the color code is it's very natural to talk about how you would go from physical qubit operations to logical qubit operations, at least as far as the Clifford gates are concerned. For the Clifford gates, you would just apply like a single qubit gate bitwise. And so that's what we call transversal operators. So if you wanted to, say, apply a logical phase gate, you would just apply a phase gate to each individual qubit. And that's very natural in trapped ion systems. This is just like running a global beam on all of your qubits. Similarly, if you wanted to run a logical CNOT gate between two logical qubits, you would just apply individual CNOT gates between the qubits in the physical qubits in your logical qubit 1 and your logical qubit 2. And the great thing about transversal operations is it's also scales in a very clearly fault tolerant way. So I mentioned we don't want spreading of our errors, right? If we have a single error, we want, after we run a gate operation, to only have a single error per logical qubit. And this is clear in the case of single qubit gates, right? If you have an error on one, since you're not doing any sort of entanglement, you just have a single error propagate through on the original qubit that had the error. And if you, in the case of a 2 qubit gate, if you have an error on one of your qubits on your control bit, yes, that will propagate to the bit that you're then going to flip based on the control bit, but that's, again, only a single error on your second logical qubit. So each individual qubit will only have one error. Cool. And last, before I end it and let the speaker present, is this conversation of universality. So I mentioned that the Clifford gates, it's very straightforward how to implement them. You just implement them transversally, but as most people know, that doesn't allow you to do arbitrary operations. So this is not a universal quantum computer yet. In order to do that, typically people implement a T-gate. And so the set of Clifford gates plus a T-gate allows you to do arbitrary operations. Unfortunately, you can't implement it transversely. And you also, even if the Clifford gates and the set of transversal gates were not the same as they are in the color code, you can't implement only transversal gates to get a universal, to do arbitrary operations. So you still would need to do this, but in order to do this with in our system, people typically do something that they call magic state distillation. So that's where you take ancilla qubits, you encode this, what they call a magic state, and using quantum teleportation, you encode a T gate onto your logical state given a specific measurement of your ancilla. Cool. And that's all I had to say before now handing it off to Ciaran Ryan Anderson from Quantinuum, formerly Honeywell.
Thanks. Thank you very much for that. All the nice introduction slides and whatnot. Sorry, I'm distracted by not used to Zoom. Hopefully, Zoom quit unexpectedly. That's not good. Don't send, and hopefully it seems to be still working.
Yeah, you're still here.
Okay, cool. And you see my slides? Okay, cool.
We see actually your power. I guess it's PowerPoint in not in presentation mode, in the what should I say, the view mode where you see the slides on the left side.
It's still showing like that? Okay. It looks different for me, but I'll try. Sorry about that. Let me try this. Does it look good now?
No change for me.
Okay. Stop sharing. No?
This looks good.
Much better. No, that was good, but now you're gone. And you're muted.
Yeah, it just kicked me out of Zoom. This is fun. Okay, attempting to share again. Is it working?
Looks good.
Okay, cool. Thanks. Yeah, so yeah, thanks for all the introduction and all the introductory material as well. So yeah, I'm Ciaran Ryan Anderson. As Nicole mentioned, formerly part of Honeywell Quantum Solutions, and now we've merged with Cambridge Quantum Computing to make this new company called Quantinuum. So that's how you pronounce it. And so, yeah, I'll be talking about our experimental realization of real-time fault-tolerant quantum error correction on the STEAN or color code. So as Nicole mentioned, in the future for large-scale quantum devices that we all dream about, that allow us to do more complex quantum algorithms, we need very low error rates. For example, breaking RSA, you might need 10 to the 12, maybe 10 to 11, depending on how you implement it. CNOT. So you need an error rate that's below that in order to, per operation in order to implement these things. And one key way to do that is to use fault-tolerant quantum computation. And within fault-tolerant quantum computation, which is all about computing while dealing with faults in a way that doesn't break your computation, doesn't cause an error to the overall computation. Within that is quantum error correction, a major tool of fault-tolerant quantum computation. So once again, it's just about using redundancy where you encode the qubit information into many other qubits to create these logical qubits. And I'll steal an analogy by my former PhD advisor. In large-scale quantum error correcting computers of the future, it's most likely going to be a lot like the Saturn V rocket, where the majority of what it's doing is just getting you there. But the actual science that you want to do is just this tiny little piece up top. In this case, it's the return vehicle and the linear module that actually does the science. But in large-scale devices, You might have like user supplied algorithm that then goes to this large, maybe millions of qubits or thousands of qubit machine, where different parts of it, all the resources are being dedicated to the quantum error correction. A lot of the time is spent doing quantum error correction because you need everything encoded in these states, and you can't just measure the states directly. You have to do the entire computation using in a fault-tolerant quantum error correction fashion. So part of the machine might be dedicated to these magic state factories, these non-Clifford states that was mentioned before, or as well as other parts might be doing logical Clifford gates or poly operations, and then you might have other parts that are just there as buffers for logical memory and so forth and such. So a lot of resources are going to be dedicated to quantum error correction in these large devices. So it's really crucial to start thinking about, now that it's still early days, to start realizing these pieces that lead to this large scale device that we kind of dream of. And what we had is this H1 ion trap with 10 physical qubits at the time. It's now since been upgraded to 12 physical qubits. By the time we had 10 physical qubits, the actual qubits are these ytterbium ions, while we also have these barium ions for cooling. And we have, so this is a schematic of the ion trap. We have these 3 different gate zones that allow us to do these 2 qubit gates, and as well as single qubit gates, mid-circuit measurements, and reset. So, and then we just shuttle the qubits around using these transport operations. So it's a shuttle-based ion trap. So that allows us for all-to-all connectivity and to be able to move the qubits around so that we can do these mid-circuit measurements and so forth. And we also have the ability to do like real-time classical information processing. So we can actually get the information from the measurements, do some sort of classical information processing, like maybe a simple Boolean functions, but or eventually more advanced things, and then feed forward that information and actually condition quantum and classical gates later in the circuit. So there's a lot of interesting technology going on that I'm amazed at, because I'm a theorist, and it's just amazing what the experimentalists can get working these devices. And so given that we only have 10 qubits in the trap at the time, and we want to move towards these large scale devices eventually. We thought about, okay, what sort of things if we were restricted to a single logical qubit, because these 10 qubits and this variety of technologies allows us to actually implement when using like the color code or the Steam code. And this is sort of the list of things that we would want to do if you restrict a single logical qubit down to, or think of the entire fault-tolerant large-scale device and restrict it down to a single logical qubit. So this includes logical preparation, so like preparing a logical 0, as well as a non-Clifford state like the magic state, so T(on+), as well as logical single qubit gates and logical measurements. Now, this first bit in the sort of the recipes of things that you want to do for a logical qubit have already been done by Nig et al. With the Steam code, or the distance 3 color code, and Egan et al. More recently with the Bacon-Shor code. However, for those, they did at most a single round of syndrome extraction, so measuring these operators to sort of detect, so like these joint ZZ, Z or XXX operators to detect errors. They only did a single round of that. But in general, for a lot of protocols for QAC, you need to do this multiple times in order to be able to be fault tolerant to at least a single measurement error. And so we want to do a fully fault tolerant QEC cycle where we're at least measuring more than these syndromes more than once. So that's a new thing that had yet been done for a full code that can correct for both phase and bit flip errors at the same time. And then we also, something that has yet been done for a full code is real-time determination of corrections. So while you're doing a computation, you're doing these arbitrary long computations, you want to take these syndrome measurements that you made of these checks that you're measuring, and send that to some sort of classical decoding algorithm in order to determine corrections. And in the past, for full distance codes, full QEC codes, the experiments have just run the QEC protocol and did the experiment, looked at the results, and determined corrections after the fact. So we don't want to do that, because we want to imagine a full large-scale device. So we need to come up with these corrections during runtime. So that's another thing that we aim to do. And the next thing is kind of a nice to have, but not really a strict requirement. But it turns out that you don't actually have to apply these corrections physically, as long as you're doing Clifford operations. So logical Clifford operations. So the corrections are basically whether you apply logical X, Y, or Z to the logical qubit. And so long as you're just applying logical Clifford operations, you can push those Cliffords through and get just, Clifford just, a commutation by Clifford just changes a poly to another poly. So you just can update these poly, store those corrections in software and just update them in software as you're doing the computation, until you hit something like a non-Clifford gate that doesn't have that property. So what we want to do is track these corrections in real time in software, and then apply them physically as needed. So take that correction out and then apply the correction conditionally using a physical logical, or apply it physically using a logical operator, like logical X, Y, or Z. And then we also want to repeat this entire thing. So we want to repeat these QEC cycles over and over again arbitrarily, because that's what you would do in a general computation. So that's what we set out to do. We, however, yet to have sort of broken even where logical operations start to outperform physical operations, because it's still kind of early day. But as we'll see later in the talk, we through the experiments, we're learning how actual, logical codes, QEC codes, logical qubits work in real experiments, and we're able to learn more about what we might need to do in the future in order to pursue that. So this was already covered, so I probably don't really need to go into it, but as was mentioned, for the color code, for these so the circles in these diagrams I'm going to be using represent the data qubits, and then you use ancilla qubits in order to measure both these joint XXX measurements as well as these ZZC measurements. And so the circuitry looks something like this. And then you have these logical operators like logical X, which is just applying X on these set of qubits here. And then a logical Z is like applying Z on these set of qubits here, this blue line. And then this was also talked about, but we'll get into the actual circuitry that we implemented in order to be fully fault tolerant. So if you have a single error occurring on data qubit 7 here, what will happen in these circuitry is this X error will propagate down through the circuit, and then will get measured by this measurement in the Z basis, and you'll get a -1 result, because the trivial results that you measure from these measuring these operators are all +1. So as soon as you see a flip in those measurement results, you're detecting a possible error. It could be due to a poly error in the circuit, or it could also be due to like a measurement error in the circuit. So for this particular X gate or X error we see here, we get these set of syndromes whenever we measure the Z checks, the Z parity measurements. We get plus, plus, minus. And so that kind of indicates that since this is the most probable error, a weight 1 error is more probable than a weight 2 or 3 error, and so on, then the most likely correction that you should choose is to apply an X here on data qubit 7. However, you have to deal with these funny things called hook errors. So this code, this distance 3 code, is supposed to be designed to deal with any weight 1 error. However, given the actual implementation using the circuitry, there turns out to be certain error locations in the circuitry that can propagate, even though they start out as weight 1 errors, they can propagate through the circuit and actually become weight 2 errors. And this, once again, given the nature of this weight 2 error that gets applied to qubit 2 and 3, it flips because 2 odds two flips make it give you an overall plus syndrome value, this +1 up here on this green check, and also this +1 on this blue check down here. So because they're touched twice by the X operators, they flip twice, and they're good. They don't detect an error. However, this check over in this corner, it only flips once. It's only touches one of the X errors. So we get this plus minus outcome, just like the previous slide we saw here. So the previous, so we get the same syndromes as mentioned in Nicole's talk previously, but you have different errors. And the correction that you'll end up doing is because that weight 1 error is more likely, is you'll apply an X operator here to correct the code, and that will end up applying an overall logical error. So the physical errors plus the correction will cause a logical error. And that's not good, because we're supposed to be fault tolerant and correct any weight 1 error. So that's bad. So because we're thinking of this whole large scale fault tolerant device that we want to imagine in the future, we need to be fault tolerant to these weird hook errors. And so we use a scheme by Reichardt in which we use something called flagging. I won't get too much into it, but essentially what we're doing is we're measuring multiple operators at the same time. So we're using 3 ancillas. So we have 7 data qubits and 3 ancillas for a total of 10 qubits, like we have in the machine. And that's why this is sort of an interesting / ideal code to look at the time. So using these 3 ancillas, we kind of measure in parallel 3 different checks, 3 different XXX and ZZZ operators at the same time, and couple the ancillas in a way so that the errors propagate through the circuit and indicate potentially these malicious hook errors. And then what you have to do is condition, if it turns out that we get, and this probably should have minus signs on them, but whatever. If this ends up indicating that there might be a hook error, because some errors will give you non-trivial results even if they're not a hook error. If we get non-trivial results from this flagging, what we have to do is condition on that. We then have to remeasure all the checks using sort of these naive circuits in order to sort of distinguish between these hook errors and non-hook errors. So that was going through it pretty fast, how these hook errors work, and you could read Reichardt's original paper, as well as, if you want, our paper, because it has a lot of flow diagrams and explanations and also pseudocode for you to look at to actually see all the details of what we implemented. So please check that out. It should hopefully be an easy read. It was meant to be not really dense, but actually sort of a cookbook of how to do this. So using Reichardt's scheme and also this fault-tolerant initialization scheme by Goto, this is our overall QEC, repeated QEC cycle experiment. there's a lot going on here, so I'll actually just step through what we did rather than just point and explain all these lines and things going on. So at the beginning of the repeated QEC cycle experiment where we're doing real-time correction, what we want to do is fault-tolerantly prepare a logical qubit. So what we do is we use Goto's scheme to do this. And in particular, it's composed of basically an encoding circuit. So encoding circuits take you from like a physical qubit where you have some general information and encode it into a larger logical qubit. So this encodes a logical 0. We then use this, we then basically measure a logical operator, a weight 3 operator, in a way that will herald particularly bad errors. So it will make sure it'll give a non-trivial result if there are weight 2 errors, which we're unable to correct for this size of code. So you can have larger and larger color codes, but right now we're doing this distance 3 code that's only guaranteed to detect and correct weight 1 errors. So this is able to eliminate, or at least, for the given that a 1 error event occurs in this circuit, it guarantees that it will flag a weight 2 thing. So what we saw in experiment is that this verification step succeeds 97% of the time. So 97% of the time we're good and we can keep on going. However, using our conditional logic that we can do, the feed forwarding that we can do in the device, if that doesn't succeed, we just repeat this again in runtime and reset all the qubits and then retry it. And what we found is, given the probability of success for the verification step, we only need to do it up to 3 times in order to reduce the to get the probability of a successful preparation to be higher than the probability of the fidelity of the logical qubit. So yeah, we repeat this up to 3 times, even if we almost always that is all that's needed. But there are a few cases in the experimental results where we saw that it actually failed, but we just keep on going with the computation. So there's no post-processing in this at all. We're doing all this live and in real time. So we're repeating this and basically doing a repeat until success algorithm here. And then what we want to investigate are the different logical polybases in order to sort of understand how, with these QEC cycles, how the different errors in these different bases affect it, in order to basically investigate the error channel in between the initialization and measure out. So we apply these transversal gates, as was mentioned before, in order to which does any single qubit logical Clifford gate in order to rotate to any of the 6 logical polybases. And then we continue, and this is sort of the heart of the experiment, all this repeated QEC cycle stuff. And so this is a flow chart that we see here because there's a lot of conditional branching going on. So this box in general represents a QEC cycle that we're doing, and we enter it here where we're measuring the XXX check and the ZZZ check here and the ZZZ check here in parallel using that flagging scheme I mentioned previously. And then what we're doing is, after we've measured these syndromes, these flag syndromes, we compare the results to previous QEC cycles. If there wasn't one that hasn't defines the syndromes, hasn't measured the syndromes yet, then we just assume the trivial case. So we're actually looking at the change in syndromes, the change in these measurements, because we're only dealing with the error within that QEC cycle, and we assume the previous one has come up with a correction and dealt with it. So then we just need to look at what has changed, what's the new error in the next QEC cycle. So if a change in syndrome has occurred, then we conditionally branch off of that, and we measure, as I mentioned before, all six parity checks. We measure all 6 of those again without the in an unflagged manner, so without this flagging. Otherwise, if no change has occurred, no error has been detected, we then move on to the another, different pair or different triplet of measurements to make. So we measure Z-type check, an X-type check, and an X-type check in parallel, using the ancillos to give us to kind of indicate those hook errors. So we're using this flagging scheme. And then once again, it's the same sort of story. We compare to previous syndrome extractions, previous measurements, QEC cycle measurements, to see if there was a change made or not. If a change has occurred, once again, we remeasure all 6 checks. Otherwise, no error has been detected, so we're good, and we can move on to the next QEC cycle. However, if either one of these things has landed us over here, and we've measured both either this one or both of these checks, and we've measured the checks in here, we take all that syndrome information and we send it to a classical decoding algorithm, which in this case is just a 2-step lookup table. So it just looks at the measurement results and tells you what the correction is. One is just for not considering the flagging information, and the other is considering both the flagged and unflagged syndromes in order to correct for hook errors. So we do that in real time at the end of each QEC cycle. And then given that we've measured these flag circuits, we then define that as our new set of syndromes that we've measured. So we take it from the unflagged circuits. And this decoding algorithm, it comes up with a correction, and we save that correction in software and continue. If there are previous corrections, we then just multiply the polys together to come up with our new correction. So we keep on updating the correction as we go. And then we just repeat this arbitrarily. That was a lot of things going on. So I don't know, I guess if the format is to ask questions in the middle, but if maybe I'm breaking what the normal format is, but if you have questions, feel free to ask them. I'll wait a few seconds for an awkward.
I had one question. So when you were talking about repeating the state preparation cycle up to 3 times,
Yeah.
I didn't understand why there was a limit and why you kept going even if it failed on the 3rd try.
Yeah, so right now the way it works is we don't have general while loops. In the future, that's something that we would like to add. So it kind of has to be a bunch of if statements kind of unrolled and written in the code. So it's conditionally at the time of the experiment, what it's doing is conditionally applying gates or not. So it's the program and the quantum computer is moving through the quantum circuit, and then if the condition's not met, it just doesn't apply those gates, and then it just keeps on going on. So it still waits that time and does all the transport, but just conditionally applies the gate. In the future, we're moving towards eventually, having a generic while loop, but you have to worry about, how long these things sit around and whatnot.
So it's like a classical software / hardware.
Yeah, and that should be, in the future, it should be, available to just, but right now it's basically you have to unroll it.
Okay, thanks.
Yeah, but still a bunch of conditional if statements and effectively doing, that stuff. But we found that it like the probability of this failing is extremely low. I forgot exactly, I don't have the numbers in my head, but it's like 99.995 or 7 or something or other percent of the time the verification step works. That's separate from what's the fidelity of the state that you get out afterwards. So what we did is we tried to get the verification down low enough so that it's not really affecting the results of the fidelity of the initialization step.
I had also, sorry, Ciaran. I had also a question about, so typically if you're thinking about fault-tolerant quantum error correction, you need to also worry about the readout, that there's an error in identifying a state. Is that flag scheme somehow circumventing that, or?
No, it's doing it. So
Okay.
yeah, it turns out because of this conditional nature, you're also protected against measurement errors. Because it's right now it's fault tolerant to a I guess an a poly error or a error or a measurement error. So it's considering it's not fault tolerant to them separately. It's if a measurement error happens, then it'll trigger the second round and you're remeasuring the checks. So there probably, there are other schemes in which you can use the color code or the surface code where you can be fault tolerant to X and Z errors separately, as well as measurement errors separately. So this is kind of still fault tolerant to one error, or yeah. So yeah, it's the conditional nature. So if a measurement, if a measurement error happens here, then it's going to trigger this. And so if one event happens, then we're going on to here and we remeasure it, and we're going to act as though this is sort of an ideal step or ideal measurement, because we don't trust the previous step. So it turns out to be fault tolerant measurements. Yeah.
Okay, great, thanks.
I have a question.
Yeah.
So
I had one more question, if that's okay. I guess I missed at the beginning the number of bits that you have here, but do you have enough to do a 2-level hierarchical version of this code with 49 bits, or is that out of
49
the realm
of? I might not be clear. Are you talking about?
So you can build a hierarchical version of this code, I'm assuming, with 7 times 7 bits for a single logical bit, right?
Concatenation, yeah. So we probably wouldn't, like, you can do concatenation, but another what you might want to do, another way to do it is just increase the size of this code. So there's a distance 5 version where you have the number of data qubits along the edge are 5 by 5 by 5. So you can make them larger and larger. So this is a family without a code family without concatenation, but you could concatenate as well. I worry a little bit about concatenation because it starts to make all the checks kind of crazy and whatnot, but that is definitely because you have all this multiplying of checks and things, so it becomes non-local. Might not be so much of a problem in our setup since we can move things around, so that's definitely something that we should explore in the future. But yeah, there's different routes. We don't currently have enough qubits to do a concatenated version of this code, but a distance 5 code, I think it requires, doing math. I'm blanking out on the number of qubits, but it's like, I want to say it's either 21 or 17 or something like that.
Well, I think the thing about the concatenated one is it's still really easy to do computations on encoding state, right? But that is not is that as easy with the distance 5 code?
You could concatenate the distance 5 code, so that then you need 5 times 5 is 25 as well. Yeah, you can, in general, you should be able to concatenate whatever code. It just might be more qubit efficient to not do concatenation and look at a larger family. But the 5 qubit code that you're mentioning isn't a family, so you would need concatenation there.
Okay. All right, I'll let you go on. Sorry.
Sorry. Yeah. Was there another? I thought I heard someone else.
Yeah, I have a question. So you said that like the hook arrow is what made this like more complicated, right? So the hook arrow is like 2 single qubit arrows, but like happening at the same time on 2 qubits. Is that correct?
Yeah. In this particular example, it's a weight 1 error that. Yeah, from what I'm seeing, this is a weight 1 error that probably was generated by this CNOT. that then propagates and becomes a weight 2 error. You do have to worry about, so a code should be fault tolerant to one error event. So it should also be fault tolerant to like a weight 2 error on the C naught itself. So if there's an X and X error, it needs to be fault tolerant to that. And it turns out the scheme is. But it turns out that there's also weight 1 errors that end up with these hook errors as well.
But like the code distance of this code is still 3, so that means you still only correct single qubit error.
It's guaranteed to correct weight 1 errors, but it can correct higher weight errors. And it turns out that it can correct for the weight 2 errors on the C naughts, not generic. Like if you have general 2 qubit errors at any position, it's not necessarily guaranteed to correct that. But it turns out that if you have specifically a weight 1 error on the C naughts, or sorry, a weight 2 error on the C naughts, you can correct it. So general weight 2 errors, it's not guaranteed, but it turns out it can for specific C naught weight 2 errors. Sorry, that's kind of like mangled how I'm saying, but hopefully get the,
That answers my question. Thank you.
Yeah, and that's important because you need to, like, that's a P, a weight 2 error you imagine as a P squared event, but a single error event is just a P event, and you want to go from whenever you're doing a distance 3 code, you want to go from eliminating all those P event errors and quadratically suppressing everything so that you just have to deal with P squared events, P squared type errors. And so you need to deal with these, since the 2 qubit error is a P error, like it's a single error event, you need to deal with that in general for D equals 3 codes. So that's actually a requirement in general for D equals 3 codes for fault tolerance. Okay, yeah, sorry. Any other questions while I'm at this stage? And then I'm sure there's more time afterwards. I think we're scheduled for. Okay, I'll move on. So these green boxes kind of just are highlighting the fact that there's a lot of like conditional branching and interaction between classical and quantum going on, and also classical classical processing of information. So we need to know the change in syndromes and feed that forward and condition our quantum gates on that, as well as in real time we need to run the syndromes through this classical decoding algorithm. So that's just highlighting all the classical quantum interactions. And then finally, once we're done with these repeated QEC cycles, which we do arbitrarily, we then move on to the destructive logical measurement at the end. So we then, once again, apply this transversal single qubit gate. So it's just some logical Clifford gate in order to rotate to the right measurement basis, because we measure in the Z basis. So we need to rotate to the right logical basis, rotate to either X, Y, or Z measurement, depending on the state that we try to prepare. And then this final destructive measurement gives us 2 sets of information. From multiplying the representation of the logical operator that we're measuring, and multiplying those values together, you get the logical output. It's effectively plus or minus 1, or if you think in terms of bits, 0 or 1. And it also gives us some information about syndrome. So effectively, it's collapsed to a classical code. And so we have information, syndrome information in one basis, so either in the X, Y, or Z basis. And so we have, we can once again send that information, those syndromes that we made from the destructive measurement, to a decoding algorithm, which gives us a logical polycorrection, whether apply logical X, Y, or Z. And so we combine the previous corrections, we take the previous corrections in real time and multiply that with the final correction that we determined. And then that basically, given the basis state that we're in, tells us whether to flip the final output or not. So Then a success of the experiment is if the result, the +or-1 final output after correction, is consistent with the state that we tried to apply. So if we try to initialize. So if we were trying to initialize like logical 0, we would expect a success would be that we got +1 back. However, if we tried to initialize a logical 1, a success would be to get a -1 back. And so all of this is done in real time. We just we let the system do it in real time, and then I finally get the information back about the success or failure, as well as information about what correction it ended up wanting to apply and whatnot. But yeah, there's no post-processing. It's just all done in real time, which is really cool. And this is sort of the experimental results that we got from doing this. So we see in this plot, it's going from 0 QEC cycles up to 6 QEC cycles. Just chose to end there. 0 QEC cycles means that we didn't actually do a QEC thing in between, but we did do this initialization and measure out. So that's like logical span. And then we have this logarithmic scale with the logical error rate, and then completely random is 50%. So in this plot, the lighter data points, what we did is we broke, because in experiment, unlike in theory land, there's variation, the variation due to the noise, or the environment fluctuating and so on. So we broke up the number of shots, the number of runs that we're doing into different chunks, and we kind of looked at the spread of that using jackknife resampling. From that, we calculated the average as well as the error bar. So the error bar is a 1 standard deviation of sort of the indicating the variance in the experiment. And then the darker points are the average. And then those solid lines that we fit each of these points to is basically an exponential decay curve that asymptotes to 50%, since that's completely random. And I also failed to mention that you see, based on this key over here, that we're looking at each of the 6 logical polybasis states. And we see a little bit of a spread, a deviation. We see that the plus and minus of each basis is roughly like on top of each other within error bars, but there is a difference in the spread of the X, Y, and Z bases, and that's consistent with what we know is our largest bias noise, which is this, which is a dephasing noise. It's effectively applying a Z rotation on each qubit. So there's additional Z noise that's the most biased noise in our system, and we see that spread is consistent with having that bias. So that's good to verify. Nothing else weird is happening. And we see that these the circuit depth is rather large, like at 6 QEC cycles, it's up to 323 C naughts, although we are applying them conditionally. So maybe about half or more of the time we're applying half the syndrome extraction. So actually, I think 80% of the time, if I remember right, we actually were able to calculate that 80% of the time no error is detected in each QEC cycle. So 80% of the time it just does half the thing. It applies half does half the syndrome extraction, does one round of syndrome extraction instead of the other, but it's still waiting around. So it's still an indicator of the circuit depth and how much the qubits are waiting around for. And so, we have this exponential fit that we applied, but you can solve for the probability of logical spam, as well as the probability of an error the probability of an error in the logical spam. So the logical state initialization and destructive measurement out, and then the probability of error in a QEC cycle. So you can plug that back in and then fit that. And from what we get, if we do 1 minus that error rate, that gives us the fidelity. So we see that we have fairly high fidelities for both of these things. We have actually, on average, slightly higher fidelity for logical spam than physical spam. But we have a error rate of around 2% on average for each basis. So it's not yet, our largest error, as mentioned before, is like the 2-qubit gate, and that's still higher than the 2-qubit gate. I think the 2-qubit gate's like something like 99.5, 99.6, somewhere around there. So there's at least 2 nines, and we're not quite there for the QEC cycle. So it's still the early days, but we want to make sure that we can, start doing these things and learning how to improve them so that we can move on to large-scale quantum computing in the future. And then, are there any questions on this, since this is an actual experimental data? Is there any confusions? No.
Yeah, I have a question. So
Sure.
you said like you are still expecting some improvement. So is this figure like the general trend we expect to see? Like, is it correcting? Like, is it lowering down the logical errors?
I might not completely follow. So in general, in general, we should see a decay. Even if you're below what's known as the threshold or the pseudo threshold, you'll see a decay until the distance of your code goes to infinity. So you'll always, in some practical term, or in the practical world, see a decay in the fidelity or the increase in the logical error rate as the circuit depth increases. But what you're trying to do is make it eventually so that this decay rate is much slower than it is for the physical qubits, and that enables you to do more logical operations compared to physical operations. So it's expanding, it's allowing you to increase the depth in the algorithms that you can do.
Okay, so like this curve is like already the trend we expect to see. We just want to make it like decay even slower.
Yeah. Okay, and then unless there's another question, on. Okay. And then, so yeah, even though we're doing everything in real time and just letting the machine do its thing, no post-processing, no post-correction, it still saves the information about what correction it did end up applying. So what we can do is back out if we didn't apply the corrections, if we threw out the decoder, what would we have gotten? So here I'm averaging, since we saw that the plus and minus of each basis state or basis was roughly on top of each other with the error bars, they're pretty close. I just combined that data. So we have these X, Y, and Z basis lines. They're just the combined data of 0 and 1 and plus and minus and so forth. And then the solid line is the experimental fit to the corrected data, while the dashed line is if we threw away the correction. So if we uncorrected it, or if we took the correction and told it not to do that from the data, then we get this. So we get a much higher error rate. That's not really saying that it's now the logical computations outperforming the physical computation exactly, because you want to compare, like, because we're introducing gates into the thing and we're causing noise, but it's showing that at least the correction is actually helping things and hurting things, if that makes sense. So yeah, we're not our decoding out. It's just verifying that the decoding algorithm is somehow not choosing, not pushing down the fidelity. It's boosting it up compared to if we just ran the circuits and didn't do anything. And so that was all the main heart of the paper, the repeated QEC cycles with real-time correction. But also to check off some of those other elements, we did a few other smaller experiments. I will go into analysis of this experimental result, at least a brief analysis using simulations, but I'll do that at the end. But first I'll get on to the other experiments. So as mentioned, we like to track the corrections in software and not apply them physically because we don't want to disturb the qubits. So anytime you touch them, you can potentially be injecting new error. However, we're just applying single qubit gates, and our single qubit gate errors are pretty low, so it's not really harming it that much. But still, if you can do it, might as well track the corrections as much as you can in software alongside the quantum computation, and then only apply them if needed. And that if needed includes whenever you're applying non-Clifford gates. For example, if you're using that gate, T-gate teleportation that was shown previously by Nicole, so if you're applying T on it using the gate teleportation, then you have to either adapt the T-gate to include the correction, or you have to apply the correction directly before doing the gate, and sort of, then you'd zero out your software tracked corrections because you dumped it all into applying it physically. So what we did is we ran both the thing that we've done before we did software correction. We've been pushing this correction through and tracking it through software, and also compare it to if we applied the correction conditionally in front of the gate. And so we applied a physical S gate, and so this is sort of serving as our T gate. So this is still a Clifford gate, but it's kind of taking it in place of the T gate. Since we have restricted to one single qubit for now, we need to do gate teleportation to apply the T gate. And so in this experiment, what we're doing is just initializing logical plus state. Then we run one single QEC cycle in order to generate corrections. And then we do conditionally, we either just continue to track in software, as I mentioned, but if we do that, we have to rotate the corrections. So we have to rotate either the X, Y, or Z correction because we're applying an S gate. So that S gate, it leaves Z alone, but I think it rotates, I'm gonna get it wrong probably, rotates maybe X to Y, I believe, something like that. Or we, in another set of experiments, we just applied it conditionally. We took the software tracked correction and then conditioned on that software tracked correction, we either applied logical X, Y, or Z physically. And that's just a weight 3 operator. So there's 3 single qubit gates that are getting applied in order to apply that correction. And then we apply the physical S gate, and then we do another round of a QEC cycle, and then we rotate the measurement basis to the Y basis, since S rotates plus to plus I, and then we destructively measure it out, and we, and then we have the final software correction from this that we then apply at the end, at least. And if it's full software track correction, then we combine the corrections throughout the computation and combine it with the final correction made during the destructive measurement. Yeah, we get overall for this experiment a physical error rate of, or an logical error rate for the physical correction of 7 ± 2%. And then for the software correction, we get 8 ± 1%. But within error bars, they're basically equivalent, which is to be expected because the single qubit gate operations are so low. It's just kind of a proof of principle that we can take tracked software corrections and apply them physically. And then the non-Clifford element that we need in order to do universal quantum computation is we chose to do the magic state, in particular the T on plus logical state. And we just used an encoding circuit. So this is the only non-fault tolerant method. There are fault tolerant methods to initialize the state, but we're just going with a similar circuit as before. And so we used that encoding circuit, but this time because it's not in a polybasis state, we can't just measure the Z operator to verify that the state was initialized correctly. So it's not fault tolerant, but it can be improved through state distillation. for example, as mentioned in the previous intro. And so we then measured in the logical X and Y basis to construct the logical error rate. And we found that it's around 2.2% for this initialization, which is below the needed distillation error rate for the input into some distillation protocol, like, for example, Brabi-Kataev's distillation protocol, but there's some others as well. And so here, I'll start talking about the simulation and the analysis of the error channel. Are there any questions on like this slide or this slide or anything else? Not. Waiting a little awkward silence to see. Okay. Then I'll talk about the simulation. So we did all this experimental stuff. It's a good proof of principle, but we also want to learn from it. And one way that can really help us learn from it is to run simulations of the experiment. And in order to do that properly and to really make sure that we're understand what the system is doing, at least the simulation basically represents our naive understanding of how the experiment runs. But of course, the experiment does what the experiment does. So it's good to kind of compare our naive understanding versus the actual experimental results. And so in order to enable that, what we basically did is we create an emulator of the device. So so we write this quantum circuitry in what's known as OpenQASM 2.0, and we actually had to extend it in order to allow all these classical operations and these particular conditional things that we did in this decoding. So we have an extended version of OpenQASM 2.0 that gets sent to a compiler, which then it has knowledge, or it's responsible for figuring out like the transport steps that need to be done in order to move the qubits into the gate zones and whatnot to enable mid-circuit measurement or single qubit or 2 qubit gates and so on. So it has a bunch of all the instructions for the native gate set, what the eintrap should do, as well as how it should move the qubits around and so forth. So we took that compiler and the stuff that it spit out and sent those instructions to a simulator. So the simulator has all this knowledge of what the device should be doing, as well as this, both quantum operations as well as classical operations. And on top of that, we made a really detailed error model. So given that we have knowledge of what the device should be doing, we then went beyond just the standard depolarizing noise, but we included like this dephasing, which is basically a rotation around Z for qubit idling as well as the transport step. So the qubits are waiting around, either being transported or just sitting around while other qubits are being gated. That takes a certain duration, and while that's happening, it's dephasing. So this small Z rotations occurring. And we also included leakage, which takes you outside of the computational state. So it takes you away from the qubits being qubits to some other state, as was mentioned previously, which is pretty harmful error because then you can't do anything with them, and it can saturate the system if you're not careful. As well as measurement crosstalk, which is effectively like the light that is used to measure these qubits, kind of interfering with neighboring qubits. And potentially causing leakage or measurement-like errors as well. So for a lot of these error rates that we put into the error model, a lot of them came from actually experimentally measured error parameters or details about the microphysics of the experiment. So it's not only a detailed error model, but the actual parameters are set mostly by the experiment. The only thing that's not well sort of captured, hard to kind of define is the dephasing rate or the dephasing error, because there's a lot of different things that can go into that. So in order to get around worrying about all the details and doing a ton of experiments in order to, or which we need to do in the future, but in order to move this forward, what we did is we considered both coherent and incoherent noise. And we basically just, once we set all these error parameters, and there's a bunch of error parameters going on, we just tune this, the dephasing rate. So that's, you're doing RZ times some duration, or e to the minus I z times some duration times some rate. And so we adjust that rate until the curves line up. And what we found is that for coherent error, if we do actual RZ in a state vector simulation, we need a rate of about 0.26 hertz. While for the incoherent, it was sufficient to have a 0.4 hertz. We think that the noise probably is, well, there's a lot of coherent noise going on, and anyway, it's the more damaging of noise for quantum error correction, especially for distance 3 small codes. They're more affected by coherent noise than larger codes. So we went with, primarily for all these simulations, we went with the coherent noise 0.26 hertz. And that actually is not too insane, because during these experiments, the calibration, we had, every so often the device would make certain measurements to calibrate the system, and we had it set up so that the dephasing rate didn't jump more than 0.2 hertz. So the fact that it's around 0.26 is not, it is reasonable. So once we have this tuned in, we have, a decent simulation of what's going on. And this also, and that leads us to the next slide. But before that, I should have mentioned at the beginning, by combining the plus and minus of each basis state, we can take these experimental curves, not the simulated, or we could take the simulated curves, but you can take the experimental curves and you can reconstruct a effective logical error channel. And from doing that, what we see is that 60% of the time logical Z is being applied, and then 30% it's logical X, and 11% it's logical Y. And overall, there's around a 2.7% error. It's higher because this considers each basis state, not just a single basis state. And this is consistent, this higher Z error rate, sorry for jumping between simulation of this. This higher error rate for the logical Z error is consistent with the dephasing noise. This is the main bias noise in our system. So that makes sense. This difference between X and Y, we're not completely sure, but we think it's probably likely due to just how the circuits were implemented. So certain single qubit Cliffords are probably rotating more towards one, rotating the physical errors more in one direction than another. So that's where that comes from. But yeah, once we have this all tuned in, and that the error channels look similar for both the simulated and the experimental results, we then can think about what would happen if we were able to scale all the physical error rates. So we took this big table and we scaled it by some linear rate. And what we want to do is get below what's called pseudo threshold. So here we're defining pseudo threshold in a way where we want to think of all the logical operations that you might do to run an algorithm, and then all the physical operations you might, if you didn't use quantum error correction. So if you, and we want to compare, we want to make sure all the logical operations always have an error rate that's lower than the error rate of the physical operation that has the highest error rate. So we want, the 2-qubit gate, the physical 2-qubit gate has the highest error rate. And so we want to make sure that all the logical error rates for each of the logical operations is lower than that physical 2-qubit error rate. And that's how we're defining a pseudo threshold. And that's this dashed line. So that kind of starts to tell you that your the logical computation is starting to outperform the physical computation. And so, well, and this compares if you scale all those physical error rates here. So this is the scaling parameter. And you look at the logical error rate, the resulting logical error rate. What you want to see is whether it will, the logical error rate will ever be lower than this physical error rate, the error rate of the 2-qubit gate, the physical 2-qubit gate. And by scaling that error parameter, we see that we're not going to get that anytime soon. We have to reduce all the error rates by, 1/1000. So that's not great. We did know, we know that dephasing is an important contributor to the logical error rate. So we looked at knocking that down by 1/10 at first, and then scaling everything, including the dephasing rate. And that is our blue or triangle point line. So that didn't improve things too much more, just a little bit. We also know that leakage is a really important thing because our protocol is fault tolerant for a single error event for poly errors as well as measurement errors, but not leakage. So we're not suppressing that quadratically. So if we do 1/10 of the leakage error rate, we do see that we're able to cross that dashed line a lot sooner. And then we thought, okay, if we reduce both of them, because we know a variety of ways to reduce leakage as well as dephasing, both experimentally and algorithmically. So it gives some hope of reducing both of them. What would we get? And we see that it crosses a lot sooner, and that scaling factor is around 1/3. So we need 1/30th the leakage and 1/30th the dephasing, but we only need 1/3 of the all the other error parameters, probably at least the leading order measurement error and 2-qubit gate error rates. So that gives us great hope that, and it indicates that we really need to focus on both leakage and dephasing. Leakage we can potentially deal with through what's known as leakage repumping. It's basically you have the qubit moves into this leak state, and you want to change it from that leak energy level and move it down to one of the computational basis states. And so leakage repumping is a scheme that will drive it down to that. So change the populations so that it's in a computational state at least. And then there's also leakage reducing gadgets in quantum error correction that we can potentially apply as well in order to dampen this down. And then dephasing, there's a variety of methods. For example, you might do like Poly or Clifford twirling, and so on. So there's a variety, or also there's particular codes that are developed to deal with bias noise. That's another route. So there's a variety of routes, even beyond what I mentioned here, that could potentially reduce that. So we'll look at those in the future. So in general, in summary, kind of checked off all these things. A lot of these are actually firsts, even the individual full fault-tolerant QEC cycle, but also particularly repeated QEC cycles, and also determining these corrections for a full QEC code during runtime. Next things that we are interested in looking at is breaking even. When we start to see the logical operations outperform physical operations, we also, of course, need to scale up towards large scale fault-tolerant quantum computation. Of course, that doesn't happen overnight. So we need to look into like quantum error correction on 2 logical qubits as well as the logical 2-qubit gate. Actually, a couple of weeks ago, Innsbruck / Aachen released a paper in which they did a transversal control knot on the color code / steam code, and it's really exciting. It's really well written. I'll also be talking about in this conference Q2B about our recent work in that field as well. So you might want to, keep your ears open if you're interested in that sort of thing. I believe some of that stuff might actually go on YouTube, but otherwise, I'm sure we'll announce things and give more information on that in the future. But yeah, so now time for the spiel. So that was all the experimental stuff, and I just want to take a minute to since you're university and there's a lot of students, you're probably looking for jobs. This Quantinuum company that we've now formed, it has like about, I've heard 400 people, 300 plus are like either scientists or work in a technical field, and we're constantly hiring, and in a variety of fields. You can be, for example, AMO experimentalist, theorists in general. I'm more of a general theorist, not particularly an AMO, do quantum error correction. I guess that's covered by this quantum information theory. But besides theory and experiment, we do a lot of other technical things like optics, microfabrication, electrical engineering, mechanical engineering, software, all sorts of things. We're constantly looking for good talents, and we're expanding. So if you're interested in that sort of stuff, take a look at quantinuum.com/careers. There's a list of Quantinuum jobs on that page. You just have to scroll a little bit down. There's a link. You can also email me, Ciaran Ryan Anderson at honeywell.com. We still have the Honeywell email. I'm sure we'll get the Quantinuum pretty soon, but it should still forward to me, so that should be fine. Also, since I'm a theorist, I know less details about the experiment than I probably should. I live in theory land a lot of times. If you're interested in the experimental or technical side, you might also want, and you have questions, or you're interested in working in Quantinuum, you might want to send an email to Justin Bonet, and he's really friendly, and he'll be a good contact for that. Otherwise, you can find us on LinkedIn too. And yeah, this is just the general fields that we're usually interested in. It's not just theory and experiment, but all sorts of electrical engineering, mechanical, atomic physics, traps, and whatnot. And also there are internships available. So if you're interested in that, all sorts of internships are open. So take a look at that. And this is sort of marketing stuff about Quantinuum, but in general, I really enjoy work. They're not paying me to say this. I don't work in recruitment or anything, but I really enjoy the work environment at Quantinuum. People are really down to earth. They're really nice. You can easily interact with any people. They're not, and there's a lot of great talent. You can work across all sorts of multidisciplinary areas. I frequently work with software people. You're not really limited to who you interact with. And yeah, it's really a great environment. I'm lucky to be working there. But yeah, if you're interested in the internship stuff, you'll get paid. That's important, but also for relocation and travel, you get to work with scientists actively working in these cutting edge fields, potentially see your work being utilized in papers and whatnot, and have opportunities to travel as well. So thank you very much for the invite and listening to this talk.
Yeah, thanks very much, Ciaran. I think, Nicole, would you want to guide the discussion?
Okay, so is this the part of it where I kick out all the...
No, not yet.
Not yet?
So I think that comes later. But I think usually we have first like a a final discussion, not a final, the pre-final discussion, and then there will be the one where you kick out the PIs. So I guess there should be no, yeah, if you have questions, feel free to ask them now. I see Daniel has a question.
Yeah, so can you turn back to the physical error scaling page?
Sure. This one?
The screen is like moving slowly. Yeah. Okay. So I noticed like this purple star series will get below the P2 dashed line at about like 8x reduce physical error, right? So that means you want to reduce leakage and dephasing by 80x actually.
This is so that dotted line is if you see the x equals 1/3. So since it would be 1/30th reducing both the leakage and the dephasing. The other normal error rates would be reduced by 1/3. Where this purple line and the dotted line and the dashed line intersect.
I have actually a similar question. When you reduce the leakage and also the dephasing, you also affect the physical error rate. So shouldn't then the dashed line also move down?
That is one detail. So yes, if I was including leakage and dephasing in that, the dephasing or the leakage is so for the 2 qubit gate, there's both this depolarizing error and then the spontaneous emission error. Half of the spontaneous emission error is leakage, and the other quarter is applying X error and quarter applying Y error. So this dashed line actually, went the wrong way. This dashed line is actually the depolarizing error rate. So we're tuning just this. And actually that makes our job harder because we really the actual overall error rate of the 2 qubit gate is even higher than just considering the depolarizing rate. So the line would be shifted. The error rate should be. We're considering a case where we have less error technically, since we're thinking of just the depolarizing error. So that actually shifts it down compared to what's if you consider leakage and spontaneous emission. So we're actually in this plot making it a little bit of a more difficult case for us. but the depolarizing error rate is the sort of the leading order error rate, because half of this is the that's a 2 qubit gate. I thought that they were off by an order of magnitude. The spontaneous emission rate is like an order of magnitude lower than the depolarizing rate, and then half of that is the actual leakage. So
it's minor correction.
That's a good catch.
Okay, I don't see more questions, so I guess the PIs have to go. And